All right, so get this. We're diving into something pretty revolutionary today. Qubits.
Yeah,
You know how our computers use bits, those zeros and ones?
right.
Well, quantum computers use qubits, and they kind of throw the rule book out the window.
They really do. The mind-blowing thing about these qubits is that they can be in this state called superposition. It's like imagine a coin spinning in the air. It's not heads or tails, right? Not until it lands. It's both at the same time.
Hmm.
Qubits can be both 0 and 1 simultaneously, and that's where all this incredible computing power comes from.
Okay, color me intrigued, but let's back up for a sec. What exactly is a qubit? I mean, like in plain English.
It's the basic unit of information in a quantum computer, just like a bit is for our regular computers, but with this added twist of superposition. And Yorgo Schneeppert, in his essay, he really hits the nail on the head. It's this principle straight out of quantum mechanics that makes qubits so special.
So it's not just some theory floating around out there.
Yeah.
We can actually build these things.
Yeah. We can, although that is one of the biggest challenges in the field. And as Schneeppert points out, there's not just one way to create a qubit. We've got superconducting qubits, trapped ion qubits, even photonic qubits, and spin qubits. It's like a whole variety pack of possibilities, each with its own quirks and potential.
A qubitsu. I like that. So with all these different types, how do we even begin to control them? Is it like flipping a switch?
Not quite. We use these things called quantum gates. Think of them like logic gates in classical computing, but
Mhm.
operating on these, quantum principles. They let us manipulate these qubits, putting them into superposition, entangling them, essentially orchestrating the whole quantum dance.
Okay, hold on. Quantum J's, entanglement. Now things are getting really interesting. But before we get too far ahead, let's talk about entanglement for a minute. That's famously known as spooky action at a distance, right?
Yeah. It's like even Einstein had trouble wrapping his head around it. Basically, it means that two entangled qubits, no matter how far apart they stay connected. You measure one, it instantly influences the other. Like they have this invisible instant communication link.
Whoa, that's wild.
Uh-huh.
And this is what gives quantum computing all that potential.
Exactly. Entanglement is what lets quantum computers make these calculations in parallel, exploring a ton of possibilities simultaneously, which gives them the potential to solve problems that would take classical computers billions of years.
Okay, so we've got these qubits in superposition. They're entangled, but eventually we need an answer, right? So how do we measure a qubit if it's in this fuzzy both-at-once state?
Well, that's where it gets even weirder. Measuring a qubit forces it to choose, to collapse out of that superposition state and settle into a definite 0 or 1, like that spinning coin finally landing on heads or tails. And here's the thing. The act of measuring actually influences the outcome. It's this core concept in quantum mechanics, the collapse of the wave function.
Collapse of the wave function. Trying to picture that in my head. Is there a way to visualize it?
You could imagine a wave spreading out,
Yeah.
and it's representing all the possible states of the qubit. Then when you measure it, it's like the wave suddenly collapses down to a single point, a single state.
Okay, I think I'm getting it. But it also sounds really delicate. Like if we're constantly measuring, are we losing some of that quantum magic?
Yeah, we are. It's one of the big challenges with quantum computing. Holding on to that fragile state of these qubits is a constant battle.
So we have these incredible qubits with mind-blowing potential,
Yeah.
but they're also incredibly susceptible to interference. What are some of the biggest challenges we face in harnessing that power?
Well, one of the biggest, and we've touched on this a bit, is decoherence. Think of it like this. Qubits are incredibly sensitive, like a perfectly still pond. The slightest disturbance, heat, vibrations, stray electromagnetic fields, it can cause ripples, disrupting their delicate quantum state. And that's decoherence, and it can basically wreck a quantum computation.
So decoherence is like this constant threat, right? Trying to mess up our qubits and their delicate dance. So what are researchers doing? How are they protecting them?
It's almost like they're building these fortresses around the qubits, these little isolation chambers. For instance, superconducting qubits, the ones that Schneeppert talks about, they need to be kept super cold. We're talking fractions of a degree above absolute 0.
Really? That's colder than space. Why so extreme?
Well, it's all about minimizing those disturbances we were talking about. At those ultra-low temperatures, the materials start exhibiting superconductivity, meaning electricity can flow with 0 resistance. And that creates an environment where the qubits are less likely to get jostled out of their quantum state.
Ah, so it's like creating this, like a super Zen meditation chamber for the qubits.
Exactly. And it's not just temperature. They're also shielded from all those stray electromagnetic fields, any vibrations. It's a huge engineering challenge to build these systems.
Speaking of different types of qubits, Schneppet's essay also mentions ion trap qubits. He said they have this incredible precision and stability. How do those work?
It's a completely different approach. Imagine using electromagnetic fields to trap individual atoms, or rather ions, which are just atoms with an electric charge. And these trapped ions, they become our qubits.
So we're like suspending these tiny atoms in midair?
Exactly. And because they're held in this vacuum, totally isolated, they can hold on to their quantum properties way longer than superconducting qubits. Plus, we can use lasers to manipulate them with amazing precision.
Wow, it's like a microscopic laser show manipulating these little atoms. Do ion trap qubits have any downsides?
Well, scaling them up to, really large numbers of qubits is still a big challenge. Each ion needs its own little trap. So building systems with thousands or even millions of qubits gets incredibly complex.
Okay, let's move on to another type of qubit that Schneppet describes. Photonic qubits. They use light itself. Photons, to be precise. And they're apparently ideal for communication. So how does light become a qubit?
This is where things get super interesting. So a photon, that tiny particle of light, has this property called polarization. Think of it like the direction its wave is vibrating. And we can use this polarization to represent our 0 and 1.
So instead of flipping a switch, we're like twisting light.
You got it. And the cool thing is, photons are naturally pretty resistant to those disturbances that cause decoherence, so they're awesome for transmitting quantum information across long distances.
So photonic qubits could be the key to building a quantum internet then.
That's the dream. A network where you could send quantum information securely and instantly across the globe.
Okay, last but not least, Schneppet talks about spin qubits. These rely on the spin of electrons. Can you break that down for us?
Picture an electron like a tiny spinning top. It can spin up or down, and we can use those states to represent, you guessed it, 0 and 1.
So the electron itself becomes the qubit. How do we even control something that small?
We use magnetic fields to manipulate the spin of those electrons. Usually they're trapped in these tiny structures called quantum dots. They act like little cages for our electron qubits.
That sounds like some incredibly precise work.
Oh, it definitely is. But one of the exciting things about spin qubits is that they're potentially much smaller than other types of qubits, so you could pack way more of them onto a chip, which means more powerful quantum computers.
Okay, so we've got all these different types of qubits. How do we even choose which one is best?
That's a really good question, and to be honest, there might not be a best for every situation. They all have their own strengths and weaknesses. Like, superconducting qubits might be great for near-term applications, where we need larger systems. But ion trap qubits could be perfect for really high-precision simulations. And photonic qubits, well, they might be the key to quantum communication.
So in a way, this diversity is a good thing.
Exactly. It lets us explore all these different possibilities, and we can tailor the technology to fit specific needs.
It's clear that quantum computing is still in its early stages, but I'm already seeing headlines about all sorts of potential applications. What are some of the most promising areas where these qubits could really make a difference?
Oh, the possibilities are, well, mind-boggling. One area is drug discovery. Simulating how molecules behave and interact is incredibly complex, even for supercomputers. Quantum computers could totally revolutionize this field.
You mean like we could design and test new drugs virtually?
Exactly. And that could speed up the development of new treatments for all kinds of diseases. Another area is material science. Designing new materials with specific properties is usually a lot of trial and error. Quantum simulations could help us understand materials at a much deeper level, leading to breakthroughs in things like energy storage, even superconductivity.
Wow, so qubits could usher in a whole new era of scientific discovery. What about applications beyond the lab?
We'll think about things like financial modeling, cryptography, logistics optimization. These are all areas where quantum algorithms could outperform classical algorithms by like orders of magnitude.
It's amazing to think about how quickly this field is evolving. But let's not get too carried away with all the excitement. We've talked about decoherence, but what are some of the other big challenges in actually building practical quantum computers?
Yeah, decoherence is definitely a big one, but there's also the issue of error correction. Qubits are really prone to errors, and in the quantum world, error correction is way more complicated than in classical computing. You see, you can't just copy a qubit. There's this rule in quantum mechanics, the no cloning theorem.
So how do you correct errors if you can't even make a backup copy?
It's kind of like a magic trick. We use something called quantum error correction, where we encode the information across a bunch of physical qubits. So even if one qubit decoheres or has an error, the overall information is still safe. It's like having this safety net for your quantum computation.
That's ingenious. But it also sounds like it would need a ton of extra qubits.
You're absolutely right. In fact, it can take hundreds, even thousands of physical qubits to reliably encode just one logical qubit. And that brings us to another big challenge: scalability.
Right, building these systems with so many qubits must be incredibly difficult.
It is. Right now, we're still figuring out how to build, control, and connect tons of these qubits. But the progress being made is really remarkable. Companies like Google and IBM are already building systems with hundreds of qubits.
It sounds like we're right on the edge of a quantum computing revolution. So much potential, but also so many challenges ahead. Let's dig into those challenges a bit deeper in the next part. All right, so we've covered the amazing potential of these qubits, but also all the hurdles in building these practical quantum computers. Let's really dig into those challenges. Starting with error correction. You mentioned it's way more complex in this quantum world. Why is that?
Well, you see, in our regular computers, you can just copy information. But you can't do that with a qubit. It's this fundamental principle in quantum mechanics, the no cloning theorem. Basically, it says you can't just make an exact copy of an unknown quantum state.
Okay, so how do you even protect against errors if you can't make a backup copy?
Well, that's where quantum error correction comes in. And it's pretty clever, actually. Instead of copying the information, we sprint it out, like encoding it across several physical qubits. It's like, imagine weaving a safety net. Even if one qubit gets messed up, decoheres, or there's an error, the overall information can still be saved. The computation can keep going.
It sounds like walking a tightrope. How many qubits do you need to create this safety net?
Well, it really depends on the specific error correction code you're using, but it can take, well, hundreds, even thousands of physical qubits to reliably encode a single logical qubit. And this leads us back to that challenge of scalability.
Right, we talked about that before. But why is it so difficult to build quantum computers with so many qubits?
There are a few reasons. For one, each qubit has to be incredibly well isolated from its environment to minimize that decoherence we talked about. Maintaining that level of isolation with thousands or millions of qubits is a massive engineering challenge.
So, like, are we talking about building a million tiny, perfectly isolated Zen gardens?
Haha, that's a pretty good analogy. And it's not just about isolation, you also need to control each qubit, manipulate them individually, and then entangle them in very specific ways. It's like conducting an orchestra where every musician is a qubit, and they all have to be perfectly in sync.
Wow, I can only begin to imagine how complex that must be. So what are some of the other engineering challenges?
Well, just building the hardware itself is a challenge. We need new materials, new fabrication techniques, entirely new architectures for these computers. It's really a whole new frontier in engineering.
Pushing the boundaries of what's possible, not just in physics, but engineering too. But even with all these challenges, there seems to be a lot of optimism in the field. What are your thoughts on the future of quantum computing?
I'm incredibly optimistic. Just a few years ago, building a quantum computer with more than a handful of qubits felt like a distant dream. Now we have these companies, Google, IBM, Intel, they're all racing to build systems with hundreds, even thousands of qubits.
Yeah, it does feel like we're at the very beginning of a technological revolution, almost like the early days of classical computing.
I think so too. And as we overcome these engineering challenges, as we figure out how to build more stable, more scalable quantum computers, I think we're going to see possibilities that we can't even imagine right now.
Well, it's been an amazing journey for me exploring this world of qubits. Any final thoughts for our listeners out there as they ponder this mind-bending technology?
I would just say keep an open mind, stay curious. This field is changing so rapidly. The next few years are going to be incredibly exciting. The potential for quantum computing to completely transform our world is huge. I mean, from revolutionizing medicine to unlocking entirely new forms of communication and computation.
Well said. And on that note, we'll wrap up our deep dive into the world of qubits. Thanks for joining us.